Okay, so we left off, we were at oxyacids. So now what we're going to do is we're going to look at the special case, the less defined piece together. And what this means is there's no really good specific way to solve for it through hybridization, etc., like we did over here for organic or single bond molecules. So these ones you basically have to almost practice these types of structures, get kind of used to it, and pretty much almost have to memorize it. And so one of the things I've done is anytime you have certain nitrogen compounds, and right away I'm thinking, yeah, there's got to be something going on here that might not fit either the perfect octet rule or some of the hybridization type models. So let's take a look. So the first thing that we can look at, let's take a look at NO. So what we can do for that is we can look at the neutral sort of version of it. And one of the things we can do is if you look it up online or something like that, you can quickly, this is for memorization purposes. So what we're going to kind of do is look at the answer and work our way back. So we can use circular dots for electrons for the oxygen. And then we can use little X's. So notice how this is a radical. There's going to be an unpaired electron. So if this is sort of the accepted Lewis structure, the other thing I want to point out here is because both the N and the O, just like we covered in organic, the 2p, the 2s2p block types of things here, we are allowed to go ahead in Organicville and do the typical types of hybridization. So we already know that one of these sticks has to be sigma type of bond, and the other one is going to be a pi bond of sorts. And we already know that from pi bonds what we're going to have to do is use p orbitals to overlap. So, and plus we're going to have an unpaired electron right there. So we're going to have to accept this as the case. Now we can do a little quick analysis on our own. We can look at, and then the other thing we did talk about is you start learning from Organicville that when you make a double bonded, this is going to be sp2 hybridized, and that oxygen is also going to be sp2. So we have the 2p and the 2s. This is nitrogen, which was by itself. 1, 2, 3, 4, 5. Now what we're going to do is we know that we're going to be sp2 hybridizing. So I'll bring it over here. 1, 2, 3 with the remaining 2p. So these are the 3 sp2s, and this is nitrogen hybridized. That's a B. And then we know that the oxygen is also going to be sp2. So this is oxygen that's also hybridized. But oxygen is going to have, it's going to look like that to start with. And then this one is going to be 4 and then 5. So what they're going to do, we need a sigma bond. So we know that for sigma bonds we have to use the hybrid orbitals. So what I'm going to use is one of them, like that. Call that the sigma bond that we made. This is the overlap of the 2p's, that's the pi bond. And this is our unpaired electron right here. So when you're looking at this, clearly what you're going to think is you're going to have, and remember how we talked about the hybrid orbitals. So technically if we're going to talk about shape, if we had to, we'd probably suggest that nitrogen is going to do this. One of the sp2 orbitals, the radical one, will look like that. The other one will do this, and then this one will do that. Oxygen is going to overlap that way. It's going to have its 2. So you have the same trigonal planar. So this is the hybridized portions of nitrogen and oxygen making their trigonal planar things, and then you're going to have the p orbitals make the pi bond. So this is the quick little analysis that works on this, and you have to trust and almost memorize that there's an unpaired electron. We'll have to leave it at that. The other thing too, though, is that was neutral NO. So then what if somebody says you have NO negative? So looking at the same analysis, you can quickly think to yourself, well, it looks like to me in this analysis, whether you want to look at the Lewis structure, you could put it here, you could put it here, or in the diagram here. So basically put, and we won't repeat this because you know you're going to put the electron in right there. You're going to get, so you get your, what did I put a little triangle to almost say like that's the negative right there, the extra electron that we put in. 1, 2, 3, 4, 5, 6. And somebody could say, if I didn't show you that negative charge, how do you know the nitrogen in this diagram has the negative charge? So you look at the electrons, it brought to the party 1, 2, 3, 4, 5, but a 6th one is there. So it's got one extra that came to the party with, which means this nitrogen would bear the negative charge. So that's how we do it. This oxygen is neutral because we know that its normal valence, when it's an atom by itself, is 6 electrons. It shows up to a bonding party this way. It brings its own 6 electrons, so that's why it still has 6, so it's neutral. Alright, so now what we'll do is we're going to take a look at the next one in the series of nitrogen. We can look at NO2. So if you're given NO2 and you're supposed to discuss and look at bonding, that's done that way. So this one's nitrogen dioxide. So the Lewis structure that you're going to see, some of them are going to draw it this way. So you have N, put a plus and look like that. So the bare bone structure you can pull off the internet is going to look like this. So now we're going to have to start filling this in a bit. So what I'm going to do is redraw it. Maybe a little bigger just to draw in where all the electrons are, because you'll start to get used to that. So if this is neutral, I guess I could put dots for this. So oxygen normally off the periodic table as an atom will have 6. And maybe I can focus this in just a bit. Try and that might be a little better. Now, if the nitrogen has a plus charge sitting on it, then that tells you right away it has to have lost 1 of its electrons. This will be another one like this. 1, 2, 3, 4, 5, 6. And I'll make the 7th one look like a triangle. That's the negative. Oxygen came with 6, picked up an extra one, and that's why it has a formal charge of -1 on it. Nitrogen normally had 5. So if it has a positive charge, this is the weird part. You have to almost trust the fact that there is no lone pair on this nitrogen. That's why it has the positive charge. So this is the more complete Lewis structure with all of the electrons accounted for, as well as talking about why you have those charges. So yet again, if we're going to do an analysis of this, first of all, it's a radical, right? So that's true. We know one of these is the sigma style bond. The other one has to be pi. And the pi bond means, yet again, this is your thinking, p orbital overlap. The sigma one is made from hybrid orbitals. Both of these, and we could quickly write that in, they're both sp2. Because in Organicville, when you see a double bond like this, each of those atoms, even if you're memorizing sort of a rule, in a standard bonding situation like this, you would say, look, that's got to be sp2, this one's also sp2. So that gives us an indication of the analysis that we would draw out to discuss this. So I could just jump right to it. Let's look at, but notice, well, we'll start. If nitrogen is sp2, that means you have 3 sp2 orbitals. This nitrogen is nitrogen with a plus charge on it. Here's the p, right? And then I could draw in one of the oxygens above it over here. 1, 2, 3, 2p. It also has 3 sp2s. This is the oxygen, this one I'm going to draw right here, the neutral one. So we'll do that one first. 6 electrons. This nitrogen normally has 5, but because it's lost one to get this positive charge, you only have 4. Okay, so this oxygen has 1 sigma bond, which is, these are sp2 orbitals. One of them has to be hooked up like that to make the sigma bond. The p orbitals overlap to make the pi bond. Then this nitrogen has over here another one. So the hybridization of that oxygen has to be sp3. How do I know that? Because in Organicville, you start to realize that when you don't have any double bonds or triple bonds, oxygen, nitrogen, and carbon are going to be sp3 hybridized. Kind of like your 1, 2, 3, 4 areas of electron density. So we know that the hybrid model for that one will be 1, 2, 3, 4 sp3s. It's that oxygen, so 1, 2, 3, 4, 5, 6. In the 7th electron, I'll draw it this way, hence the negative charge, right? And then this one makes a bond that way. So this is the other oxygen that had the negative charge. So this is sort of the analysis that accounts for the hybridization of each of these and where the electrons are. So that will be NO2. So we did the same thing a minute ago with the NO, but now what if we were to look at, if you see it done, NO2 minus. Now notice this one was nitrogen dioxide. As soon as you do this, doesn't this ring a bell back to the memorized nomenclature oxyacids? So now I know what we're thinking is, with this analysis, it should still work for this, the only difference being this nitrogen. If the overall charge on this was neutral here, and this is what it looked like, all you have to do is put in 1 more electron, which is going to be right here. So we're probably not going to have that radical. See, there's 1 electron right there? You put another one in, so there'll be a lone pair on there. Probably, but let's see how this works out. We could have the nitrogen. Well, actually, we don't have to really bother doing this. You are going to... Yeah, we'll just use this. This lone radical electron, the negative version of it is going to have an extra one built into it, just like that. What I meant to do here was, does the oxyacid procedure work on this one? I can tell you the previous one we did, which was here. Watch what happens back here when we started with NO. Watch what happens when you try the oxyacid procedure. There's no negative charge until you get to this one, so let's try that one, the negative version. Well, the rule was you draw it like this, you put the negative charge on here, and it said double stick the rest. Well, there is no other oxygens to double stick. So you see how it fails for this one. So the oxyacid procedure fails on that one. But let's try this one. It said draw the N, put in the 2 O's, put a negative in, and then double stick the other one. Well, isn't it interesting how this is pretty much this? The only difference is we would have to memorize there's no positive charge here. And there wouldn't be, so this is going to work out perfect. It's been a while since I've done this. So you could quickly put in these dots. You would put these dots in just like that. And then you would say 1, 2, 3, 4, 5. So this works perfectly fine on NO2, and this would be called nitrite ion. So the quick and dirty oxyacid procedure works on NO2, but if you were doing the full-blown analysis, it would have been the same as NO2. The only difference is an extra electron. That was neutral. You would get a lone pair right there, and it would look like that. So that's NO2. The other thing that we could point out here, and I might as well do it now, let's go back before we move on. The interesting thing about NO, right, is it's a double bond, and we had 1, 2, 3, 4, 5, 6, 7, and this is 1, 2, 3, 4, 5, 1, 2, 3, 4, and then 5, the lone radical. So what happens if you were to double this up? Could you dimerize this? And this is one of the things that you could do. So let's take a quick look. We'll find it. I'm just going to pause. So I did a quick check here, and what's interesting is, and again, this is something that I certainly do not know off the top of my head, but looking online, what I was thinking is, I know that the next one, NO2, does dimerize. So if I could draw this like this, and I just tried to keep it a little cleaner, and I had another one, why, 1, 2, why couldn't I just dimerize these, have them connect like this? What's stopping us from doing this? 1, 2, 3, 4, 5. So you can see clearly the octet rule, if you want to talk about that one, is being followed. So I went looking for something that looked like this. And the only thing I could find, I did find this, but they didn't show the structure, the accepted structure for it. Didn't have a nice sounding name. But what I did find was this 2 minus. And the structure they drew for that one was that. So clearly what it looks like is you have that. So both nitrogens have 5. These both have a complete octet, so it looks like this. So I think you can see what I'm getting at. On paper, for NO to dimerize just like this, looks clearly like this is possible and should have no reason not to be. But again, we're in this memorize section where you have to do the footwork and look to see if the compound actually exists. But for bonding on paper, it can be, and it looks that way. So in any event, if we look at NO2, so NO2, which is what we're doing here, clearly this one can dimerize. And when it dimerizes, you're going to get N2O4. So N2O4 okay, so we were looking at, we did nitrite the negative ion. Now we're just going to take a quick look at NO2. That was the neutral one, but we noticed that it was a radical. So you could imagine 2 of these compounds. So let's draw it out this way. You would have one of them. And the other thing too about this is the shape of this one, to be honest, I know I drew it straight, but the shape of this would actually be, if we did this analysis, it's sp2, so it's trigonal. This means it's trigonal. Planar, like that. So one of them would be this, one would be that, and then the other one would be like a lone pair with the radical. So this would be a plus, and then this would be a minus. So when 2 of these bond together, you can imagine you're going to get that. And then each one of these compounds, when 2 of them dimerize, this overlaps to make a nice single bond in the middle. And then you're going to get, and both of these have a plus charge. How do we know we have plus charges on this? So if I was to rewrite this out a little clearer, make it a little bigger, and then I'll draw that one this way. So I'll use dots for this one's. 1, 2, 3, 4. This one would have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This one would be 1, 2, 3, 4, 6. This one would be 1, 2, 3, 4, 5, 6, 7. Okay. Why are these positive? So this nitrogen is missing one of the 5 electrons that it brought to the bonding party. 1, 2, 3, 4 electrons. That's why it has a positive charge. Why do the oxygens have a negative charge? 2 of them anyway. Well, 1, 2, 3, 4, 5, 6, 7 electrons. When oxygen to be neutral only carries 6. So one of these is extra. The overall molecule, N2O4, is neutral because this positive is equal to this negative. They cancel each other out, and over here as well. But this is the Lewis structure that you could draw for this. But notice how both of them, because of reasons we talked about here, when you look at the hybridization of nitrogen, carbon, oxygen, if it's sp2, it's automatically trigonal planar. So we talked about how the hybrid orbitals, regions of these electron density, 3 of them, takes precedent for the shape. The overlap of the p orbitals to make pi bonds, we just sort of, ignore that. So this is the approximate shape that we definitely predict for N2O4. So what do we have next? Well, one of the things we have is it possible, and I looked it up online, to have neutral NO3? Now, we already know that the nitrate anion with a -1 does exist, but what about this one? So when you look this up, what you're going to find is you're going to get this. So you'll have an oxygen with a negative, and then this gets a positive. So this is sort of the structure you could find on Wikipedia or something like that. So now right away we're going to work backwards a little bit here, and we're going to say, okay, well, right away one of these is a sigma, one of these is a pi. So this is the overlap of p orbitals to make the pi bond. This one is sp2 because that's sp2 hybridized. That's the other thing we realize. So to do the analysis of this one, you got 3 oxygens. So I'll give myself a little bit of room here. 1, 2, 3. 3 sp2s. And this nitrogen is plus charge. And a 2p. So it's going to have 1, 2, 3, and 4. This oxygen is also sp2. So I'm going to draw it. I'll shift it over this way a little bit. 1, 2, 3, and 2p. 3 sp2s. And that's on the oxygen. So this one's going to have 1, 2, 3, 4, 5, 6. So this one will tie in like that to make the sigma bond. The 2 p's overlap to make the pi. So that takes care of that oxygen. You get 2 more oxygens. So I'm going to cramp it down a bit. 1, 2, 3, and it's, no, it's sp3. This is sp3, and this is sp3. So what's going to be really odd, if you're making NO3, which has been observed, this one has no completed octet, which seems really weird. But we're going to have to face that. So we'll do this one first with a negative charge. So 1, 2, 3, 4, 5, 6. One of these is the extra electron. The other one bonds to the nitrogen like that. This one is this oxygen, which is sp3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And this is the other oxygen. So that oxygen, you'd have to leave this unpaired radical on that oxygen. So I guess if we're drawing another picture of it to fill in all the electrons. 1, 2, 3, 4, 5, 6, 7. That one needs 7 to make the negative charge. 1, 2, 3, 4. This nitrogen is missing one of the 5 it brought to the bonding party. This oxygen is neutral with 6. This one, we have to trust the fact, because there's no, if we trust this, there's no charge on that nitrogen, so it means it has to have 6 electrons around itself, but only one of them's in a bond. So that is, it's not called nitrate, it's nitrogen trioxide or something like that, and it is a radical. So the interesting thing is, if we turn this into the typical anion, which is very popular, we call it nitrate, right? you have one extra electron in the system rather than we had for this neutral one. And you can see in this diagram on the nitrogen, where's it going to go? It's not on the nitrogen. There's no room to put it. But you could easily put it right there where there's an unpaired electron right here. So you're going to get, much like we already talked about, the oxyacid drawing procedure. This is exactly what you would get left with. So this makes sense. So that's nitrate anion of NO3. That's the neutral version of NO3. So that looks okay. The other type of molecules we can look at in this section, they're all usually nitrogen-based because there's so many of them and they're kind of weird looking. N2O. So N2O, we're trying to memorize what this might look like, so not a bad idea to get used to what they might be. A little practice gets you into this. We're going to go over more officially resonance forms. But what I can do is we can show you how accepted alternate forms of writing this structure out. So that has a triple bond, this one has a 1. But it's almost like an arrow can show how this can move in between like this. So you could wind up with that. And what you're going to find if you do that is it's going to look like this. Sorry, my bad. This will fall in here. This will go up onto here. Two possible structures. So it's almost like in the resonant form, as we'll learn later, is the reality is something in between this. Because quantum mechanically, the electron density gets spread out and it exists the way that it is. But for the sake of what started from Lewis theory and writing Lewis structures, if you could write an acceptable alternate form, and basically what you'll learn in organic is you can move this pair up onto that nitrogen, and this can move down into here. So you'll start getting used to those arrows in organic. But for now, we'll just say, look, this could be written either way is acceptable, but the analysis is this is a triple bond. So in this one, they're sp. This one with a single bond, this one be sp3. This one, this is sp2, sp, and this one here would be sp2. That one would be sp hybridized because it's making 2 pi bonds. So it has no choice but to do that. And we'll cover that in a minute. So we'll start over here with this one. So I could call this nitrogen 1 and 2. I'm going to start with the middle one, nitrogen 1, 2. And if it's sp hybridized, that means you'll have 2 sps, and this is nitrogen. That has 4 sticks, so I missed a positive charge that has to be there. So this is nitrogen plus. So you would have, and you could clearly see what this is talking about. 1, 2, 3, 4. This is 1, 2, 3, 8. This one's going to have triangle, triangle, triangle. And this one's neutral, so you're going to have that. The 5 on that one. So this one's going to have 4. 4. So the P, this nitrogen, this one is S. I don't know what I'm thinking. This one's SP. It's making a triple bond here. So you 2 of these. So this is a sigma, and this is a pi, and this other one is a pi. So you can only make 2 pi bonds like that. So I'll draw. This is N2, and I'll draw up here 1, 2. This will be N1. It's neutral. 1, 2, 3, 4, 5. So there's the lone pair right here. So what'll happen is these 2 nitrogens will make the sigma bond that way, and then the 2 pi bonds are going to look like that. This oxygen will be over here, sp3, 1, 2, 3, 4. This is oxygen, sp3, 1, 2, 3, 4, 5, 6. The negative means an extra electron hooks on there, making it oxygen negative, and then this one will overlap with that of the nitrogen center one. So that's what this bonding arrangement is going to look like. The resonant form is a little different because now this middle one's sp, but these 2 outsides, this one's only making a double bond, this one's only making a double bond, but this one is essentially making 2 sigmas, 2 pi bonds. So this one in the middle is sp, So 2 SPs, and this would be the nitrogen, which we called 2, and this would be 1. So nitrogen 2, which carries a plus. 1, 2, 3, 4. I can put the oxygen up top, or the nitrogen, sorry. It's going to be sp2 hybridized, and that's nitrogen 1, which has a negative. So that's 1, 2, 3, 4, 5, 6. One of these is a sigma, the other one is a pi. So this nitrogen hooks up with one of those for the sigma. Then it does this for the pi. Then the oxygen is sp, so I'll write the oxygen over here sort of down low. sp2, sorry. And this is the oxygen. 3 sp2s. 1, 2, 3, 4, 5, 6. So the sigma is there, and then the pi is there. So this one is sigma, and this one is the pi. So you can see how not super well defined, because what you almost have to do is start looking at some of the anomalies of the bonding structure that nitrogen can make with oxygens in particular, especially with the radical unpaired situations we've seen. So you almost kind of have to memorize a little bit. Plus you have to get used to these formal charges that appear with a lot of these nitrogen compounds. So that's why it's almost in a good way to feel your way around what this structure is going to look like from experience, and then you can easily do the analysis, right? And it turns out that the geometry of these are going to be linear. So look at this one. I'll show you the linear geometry of that. So it's the hybridization orbitals that control the geometry. And if all you have is an sp hybridized, then what that tells me is that nitrogen number 2 is going to have 2 linear sticks. And those hybrid orbitals are going to look like this. One of them points that way, the sp. The other one will point the other way at 180 degrees. So when you look at some of your other earlier ones, if you have an sp hybridized thing, these two hybridized regions are 180 degrees apart. We ignore the p. So now we can look at, we'll go on this side, the nitrogen 1. So the nitrogen 1 was also sp hybridized, which means it's going to have a funny looking one go that way. It's going to have one go this way, which the lone pair will be in there. This one has this is now straight on overlap. That's the sigma. This nitrogen reaches out to this one, oxygen. sp3 looks like that. But then you're also going to have, this one's tetrahedral. So if this is in the plane, you would almost have to draw another one like this, and then you'd have to draw tetrahedrally 2 more like that. So you'd have one here, one here, one here, and one of these would be your negative. So now we look at the p's. There's 2. So you would say, I'm going to draw in y, and this will be the z. This will be the z, and this will be the y. So if we start with right here, one of these, if it was py's overlapping, I'll draw them small to make room. I'm drawing them small. We're just purposely showing the connections like this. That's one of your pi bonds. That was up here. The other one is going to be the other remaining p orbital, and I'm going to draw it in the z, which is supposed to be coming out as, but I'll exaggerate the size of them, right, because the z-axis is like this. I'll exaggerate the size of it just so it's easier to see what we're doing. That's the other pi bond. So this is sort of the idea of what the electron density, using this model, organic style hybridization models of what it might look like. This is not exact, it's just a model. It helps us approximate what it might very well look. Okay, so that looks okay. And if we do this one you have, this middle one's sp, so this is going to control. We know that the middle nitrogen is sp hybridized, so right away that's a linear arrangement of its 2 sp orbitals. On the one side you have an oxygen, it's sp2, so it's going to be like this, trigonal planar. And what that means is, for this one, it's going to have another sp2 with a lone pair and the other one with a lone pair. That's your sigma bond. This nitrogen will then connect with this one, which is also sp. So this one will be a lone pair over here. This one's the sigma bond between the two nitrogens. And then this one has, that nitrogen had two lone pairs because this N one was sp2. So my bad, this one's trigonal planar, that N1, sp2, trigonal planar, 120 degrees. So it'll have two more sp2s out like that because it clearly had already on that last one 1, 2, 3, 4, 5, 6, two lone pairs. And then you have the P like this. But you notice how we've used up the PY orientation. So now what I'm going to have to do is draw the z-axis out and use the z-axis for this one. So we'll draw this p orbital here, and on here we'll draw it like that. So one of them is in the y direction, so it'd be like this, and then this connection for these p's would be like this, coming out at you. If you had a molecular model set, you could look at that. So N2O is that one. We could even look at, what else do we got? We have N2O we've done. We can move on to a few like this. I think we have, well, we have N2O3, which is a neutral overall. Why don't we try this one? I don't have an official answer for this one, but if I was given this, could I come up with an acceptable? So the way that I would do this, knowing what I know about nitrogens, I'm going to stick those two together, and it's almost like you can imagine. Well, didn't we already know that you could have NO2? So NO2, as I recall, look like that. So let me go back and look at NO2 so that I don't confuse the issue here. So you're going to end up with 4 electrons on here. And I'm going by memory. I know that this was a weird radical thing. So by default, if it doesn't have 5, you have to have a positive charge on that. And to make the, so what I'm modeling here is looking at the NO2 because I knew of that. Right? So then you're going to have this oxygen, right? This one here. Since this is neutral, this is going to have to be a negative charge. But the key point is that there's a radical. We've seen that dimerize with itself. But this one looks to me like we also seen NO, which radical right there. So why don't we just dimerize those two is really what it looks like to me. So my first guess would be take these two and just combine them because they have an unpaired electron on each. So I'm going to draw it this way. And then I'm going to draw a stick. And that would be like that. So you're going to have this NO would look like that. You'd have 1, 2, 3, right. And then this would be like that. This one I could draw little triangles for. So it still carries the positive, and then this would have the negative, and that would look like that. So that would be N2O3. The analysis for this one, and let me redraw it without the dots. So the analysis, and we only draw the lone pairs and if they help us get an idea of the shape. this is what it would look like. And then you would say, okay, hybridizations. This would be sp2, sp2. This is sp2 because there's a double bond. And this is sp2. This is going to be sp3. Wherever you see the sp2s, one of these is a sigma, one of these is a pi. One of these is a sigma, the other is a pi. So, yeah, that would be N2O3. We could do the analysis on this for the bonding if you want. Sometime later you can come see me if you're stuck on that one. But I think by now we've drilled that pretty good. So now we can look at, to kind of close out some of these molecules that you have to just get some practice at doing. So let's say that in your book it tossed this one at you. In the next video we'll cover resonance. So we've already touched on the two structures. This one's going to have a resonance structure. So one of the bare bones Lewis structures you'll get. And again, this is something you have to kind of memorize a little bit. Spend a little extra time. You can't rely on the procedure to get you the exact structure. This would have a lone pair there. And what you're going to realize is this is going to have a resonant form. Two acceptable drawings, if you will. 3 bonds on that. That's an ion. This one, you are going to have negative on the nitrogen because it's going to go this way. Could I really come up with this? You'd have to play around with it, get more familiar with it, but I'm going to redraw this now with the electrons in so we get a better look at it. Well, if this oxygen has a negative, you know you're going to have 1, 2, 3, 4, 5, 6, 7. It's got one extra than it came to the party with. This one's going to be... So carbon's neutral, has 4 electrons associated with it. This one here, 1, 2, 3, 4, 5, neutral. This resonant form. So this one, 6. This is 4. 1, 2, 3, 4, 5, 6. Hence the negative. Nitrogen normally has 5, gets an extra 1. There's a negative charge on that. So the analysis for this, you can see that if you were asked to draw the hybridization analysis for this, triple bonds, they're both sp. This is going to be sp3. Double bonded things, although if this one's making 2, because we know that one of these, and we could go over here and say one of these is sigma, and then the other 2 are pi's. So you need two p orbitals on each to do that. This one's going to need 2 p orbitals because this is a sigma, this is a sigma, but the other one is a pi bond. Carbon in the middle is making 2 pi bonds, therefore this one has to be sp. This is sp2, and this is sp2. We've seen this before, type of analysis we're going to do, so if I'm drawing this one out, the carbon I can put right in the middle, but carbon is going to be sp. So it's going to look like this. The 2 sps, and carbon has 4. The nitrogen is also sp. So here's nitrogen, 5 electrons. So you can see that the sigma bond is when the sps overlap, and the double pi bond is there. And then oxygen, if I draw it down here, is sp3. So you got 4 sp3s, and this is oxygen with the negative. So 1, 2, 3, 4, 5, 6, 7. This one's the extra negative. This one can bond right there. So that makes sense of that one. And this one over here, you can see how the carbon is going to be. Oh yeah, and if I'm drawing the picture of this one down here, the central one is the carbon. The central carbon, the hybrid orbitals, there's 2 of them, which means we focus on them, we ignore the p for geometries. So if you only have two, it's going to be linear. So therefore, one of the SPs points that way, the other does that, the 2. If I go over here, the oxygen was sp3. So if I draw in the same line here, one of its hybrid orbitals like that, then I'd have to draw another one like this, another one going back, because it's tetrahedral. So those hybrid orbitals look like that, and they are lone pairs. One of them gets a negative. So then we move on to nitrogen. So nitrogen's over here. It's also sp, therefore linear, 2 sticks. Draw the 2 sp orbitals for it. One of them gets a lone pair. And what are we left with now? So now we have to do the y-axis, and then the z-axis will be for the other p orbitals. So I'll draw these ones a little bit small, the py's. So they're overlapping. That's your pi bond. Your sigma bond's in the middle. And then the z's, you would draw monstrous ones just to show that we know they're there. Right? And they overlap. Looks like that. This one we already did that. You can do that one on your own, but this at least shows you the nature of the charges and whatnot. So that looks okay. And you can see what's analogous to that. Now that was cyanate. Cyanate ion. And if you go to SCN negative, this is thiocyanate. Now, what's going to happen is you can see how sulfur sits under oxygen. So this analysis is going to end up being identical. So what you can actually see happening here is just draw these 2 structures the same way. And you could say the resonant form is when this crawls up on here, this falls down, like that. 2 resonant forms of them, and the analysis we did down here will be identical. The only difference is instead of this O, you're going to put S in its place. So that is thiocyanate. 2 more to go here. 2 more to go. Azide ion. So azide ion. Well, you're going to find out for this one a little bit of memorization. It's going to look like this, or the resonant form, where one of these is going to fall down and the other one will fall up here. So you're actually going to get a really strange, like if I was to start drawing these arrows, this is going to fall down, and a full arrow means one of the lone pairs is going to fall into there. This nitrogen doesn't have room to make 5 bonds, so these 2 electrons are going to go up here. So this nitrogen is going to steal the electron that used to belong to this one in the bond. So this is going to get a -2 charge. -2 minus. It's going to look like that. 2 resonant forms. So clearly here, this one is sp2. This middle one with 2 pi. So the first, that's a sigma bond. This is a pi bond. Same thing here, sigma and pi. So this one's going to be sp hybridized in the middle, and this will be sp2. So we've seen that before. This one, sp3, this one's sp, and this one is sp, triple bond. I can redraw this bigger, and I would have to 1, 2, instead of 5, 1, 2, 3, 4, 5, 6. It gets the negative charge because there's 1 more electron than the 5 it came to the party with. This one is a positive charge, which means it's missing an electron, so that's a positive. This is a negative. And then this one here would be 1, 2, 3, 4, 5, 6. Negative. So you can see when we draw this arrow to make the structure, a full arrow falling down into here means that both of these electrons are moving into here to make the triple bond, literally. Okay, which is what we'll see in a minute. But this needs to have one of these sticks break, because it can't have more than 4. You can't have 5. So when this is doing that for resonant drawing, we take this, and both of these electrons are going to move up onto here to give you this structure. So if I redraw that, you're going to get 1, 2, 3, 4, 5, 6. Yep. 7. Hence the -2 charge, because it came to the party with 5, now it has 7, -2. And then in here you'll have that. This is a positive, and this goes 1, 2, 3, 4, 5. So that's what that looks for azide. And then you have one of the classic ones, ozone, O3. So you start to get better and better at this as you play around with it. I don't think oxygen's going to do this. How do I know that? Again, this is by memory, because at first glance you might think this is acceptable. So when you're learning Lewis theory, they'd say this might be acceptable, so draw as many as you can and look for the better one for the rules. Well, I know from experience that's not the case. Because I know that oxygen can form 3 sticks, usually maximum, right? And as soon as you do that, this is going to be an automatic plus. So that just comes from experience. So this one's going to look like this. And again, this is in the section where you almost have to memorize this to some extent. It's not super obvious as to how and why this is the case. It's got 5. 1, 2, 3, 4, 5, hence the positive. Then over here, you'd have 1, 2, 3, 4, 5, 6, 7, hence the negative. Neutral overall. So ozone would look like that. Right? So this, I do think, summarizes a good section that I would teach in class that covers this special case where we kind of loosen up, less defined, piece together valence bond theory, a little bit of the organic, some of the single bond stuff. Plus we have to memorize the special case, especially when you have these radical things. And nitrogen ends up occupying a lot of these questions that might be in the back of your book or on a test. So you do have to memorize and get a little experience dealing with this group. So I showed a good chunk of them, which makes sense. So that about covers that.